Okay, welcome students to session 1.5. Sorry, 4.5, linear dependence and linear independence. Get into today's notes. Okay, 4.5 is linear dependence and linear independence. Okay, basically, we're going to answer the question how to determine the minimum number of vectors required to span a vector space, span V. Okay, let's start with a theorem. Okay, theorem. Let V1, V2 to Vk be a set of at least two vectors in a vector space V. Okay, then the set of is linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the others. With the others. Okay. Okay, definitions. A finite non-empty set of vectors V1, V2 to Vk is a vector space V in a vector space V. Okay, in a vector space V is said to be linearly independent if only values for which any linear combination of the vectors, which C1 V1 plus C2 V2 plus CK VK, okay, any linear combination of the vectors equals 0. I can squeeze that in here. Okay, equals 0. Okay, and that's only true. The only values for which those could equal 0 are when okay, C1 equals C2 equals CK, they're all 0. Okay, if they're all 0, then it equals 0. Otherwise, it doesn't equal 0. Okay, it equals some other vector. Okay, and the only time it would equal the 0 vector is if all the constants were 0, then it's linearly independent. Okay, theorem. Let A equal V1, V2, Vk. Okay, where each vector is in Rn. Okay. And the linear combination can be written in the form A times C is equal to 0. And okay, A times Z is equal to the 0 vector. Okay, it can be written as this, where A is an n by k matrix, and C is equal to all of my constants, C1, C2 as a vector, C3, okay, CK transpose. That just means that this row vector would really be a column vector. Number 1, if k is greater than n, then they are linearly dependent. If I have more vectors than dimensions, then they're linear dependent. Okay. Think of it like having a 2-variable equation, and you'd have 4 of those, 4 2-variable equations. Well, yeah, one of those is going to be, you're going to be able to get a combination of 2 of those to get the third or the fourth. Okay, there's some way that you could do a linear combination that would get you the third and the fourth. So if the number of vectors you're given is bigger than your dimension, then it's going to be dependent, linearly dependent. And then V1, V2, Vk is linearly dependent. Right? Number two, if k is equal to n, if you have just enough, okay, if k is equal to n, okay, then v1, v2, vk is linearly dependent if and only if, we saw this in the last section, if and only if the determinant, okay, is equal to 0. Okay, so if the determinant was equal to 0, okay, we saw that the system was not invertible. Okay. Okay, and it would not yeah, and so the number of vectors you have would not span. So it's not invertible, and therefore does not span Rn. Okay, if the determinant is equal to 0, well, it's the same thing. We're just expanding on that and saying it's linearly dependent if the determinant is equal to 0, therefore the vectors do not span, would not be able to span Rn, and therefore they'd be linearly dependent. Okay. Okay, note. For k equals n, any set of linearly independent vectors, okay. Okay, this means that you would have an n by n matrix, okay, or a square matrix. Okay, will yield an augmented matrix okay. If k is equal to n, any set of independent vectors will yield an augmented matrix that in RREF, reduced row echelon form, is okay, basically my identity matrix augmented with my zero vector. Okay, so we get 1, 0, 0, 0, 0, 1, 0, and okay, that's if it's independent. Okay, which independent is good. We like independent. Okay, we don't like it so much when they're dependent. Okay, independent's good because then I can get a unique solution. So, thus, C1 equals C2 equals C3 dot equals C n. And those would all be equal to 0. All the constants would have to be equal to 0. Okay, because we could solve, it would be 1Cn, or 1C1 would equal 0, and then all the way down. Okay, C2 would equal 0, C3 would equal 0. And what I'm referring to is this diagonal, because that's what's going to get me the C1, C2, C3. Okay, if I did 1C1 plus 0C2 plus 0C3 is equal to 0, then the only way that that's going to be true is if my constants are all 0. Okay, however, if the 0 vector appears within the matrix, okay, if there's zeros in either any row or column, appears within the matrix, okay, the system is linearly dependent. So it's kind of a quick and easy way to figure out if something is independent or dependent. Okay, if we put a matrix in REF form, a homogeneous matrix, in REF form, and we get it to be the identity matrix, then we know that it was independent. Okay, but if we get a row of zeros in that, we know that it was dependent. So pretty quick way. I say quick because we're gonna do REF, but we're gonna use technology to help us get REF. Okay. Okay, so let's do an example of this. Number 1. Are the vectors v1 equal to 1, 1, 0, v2 equal to 1, negative 1, 1, and v3 equal to negative 1, 1, 2. Okay, are they linearly dependent or linearly independent? Okay, so we start off with the fact that we have 3 variables and 3 vectors. We have 3 components and 3 vectors, which is good. Okay, if we had over that or under that, we couldn't get linearly independent. It just wouldn't happen. Okay, so it's a good start. That's why we don't know right off the bat. If we had more vectors, then they'd be linearly dependent. If we had less vectors, then it would be inconsistent, and we would not necessarily know they wouldn't be linearly dependent or independent. Okay. We just have an infinite number of solutions there. Okay, so let's look at what we have here. So we're going to take C1v1 plus C2v2 plus C3v3, and we're going to set that equal to 0. Okay. Okay. And we're going to say that C1 times 1, 1, 0 plus C2 times 1, negative 1, 1 plus C3 times negative 1, 1, 2, okay, is equal to 0. Actually, we'll let it equal the 0 vector in 3 dimensions, okay, in R3. Okay, so this is going to become C1, C1, 0, plus C2, negative C2, C2, plus negative C3, C3, 2C3 is equal to 0, 0, 0. Now I can set up some system of equations by adding the components together. Okay, I can say, well, C1 plus C2 minus C3 is equal to 0. Okay. Okay. Yeah, yeah, that's correct. Okay, and then C1 minus C2 plus C3 minus C2 plus C3 is equal to 0. Okay, good. Okay, and then 0 plus C2, okay, plus 2C3 is equal to 0. So we want to write this as AC equals 0. Okay, so I'm going to write the coefficient matrix 1, 1, negative 1, okay, 1, negative 1, 1, and 0, 2, or sorry, 0, 1, 2. And then that's going to give me C1, C2, C3 is equal to 0, 0, 0. Okay. Now I want to figure out is A is A linearly independent, or are the vectors linearly independent or linearly dependent? Well, we could do it a couple different ways. Okay, we could look for, we could put this into RREF if we really wanted to. Okay, or we could just test the determinant. Okay, so maybe I'll show you how to do both. Okay, so if we took, let's do this on our calculator. If we took the determinant of A, okay, what do we get? Plug this into my calculator. Let that boot up. Okay, let's go back to the matrix A, and let's see what we get for a determinant. Okay, because if the determinant is not equal to 0, then it's not linearly dependent. Okay, then we will say that it will be linearly independent because the only values that I could get for C1, C2, and CK to equal 0 would be 0. Let's show it both ways. Okay, so I get 1, 1, negative 1. Okay, 1, negative 1, 1. Okay, 0, 1, 2. Okay, second put out of that. Okay, I can actually just steal above here, determinant of A. Okay, and the determinant is negative 6. Okay, now, the other thing that I can do is I can REF this thing. And because the determinant is not zero, I kind of know that this is going to be linearly independent, which means when I RREF it, I should get the identity matrix. Let's see if we do get that. I'm going to go back to math here. I went to matrix and then math. Oops. Matrix and then math. I'm going to go up until I hit RREF. Okay, so I'm going to RREF A, matrix A. Oops. Okay, and I get the identity matrix. Okay, so either way, it shows that this is linearly independent. Okay, I would end up with three unique vectors. Okay, and I need all three of them. I would need all three of them to span R3. Okay. Okay, so those are unique. They're all unique vectors. So the determinant was -6. Okay, if I were to RREF that vector, I would end up with the REF A. I would end up with the identity matrix. Okay, and if I were to augment that with zeros, the zeros wouldn't change, because if I did any row operations with zero, they just stay zero. Okay, and so we could have plugged in the zero vector as well, and we would have come out with the same identity matrix on the left side. Maybe I'll show you that real quick. Okay, because we're setting up what we're doing for kind of like the rest of the chapter, and you know, I don't want you to question, oh well, you know, if it's homogeneous, then you know, maybe it would have come up with something else. You know, when it's non-homogeneous, then all bets are off. But we're just dealing with homogeneous right now. So let's change our dimensions on this. Okay, and we couldn't find a determinant for an augmented matrix because it has to be a square matrix. Okay, but we can do RREF on a augmented matrix that has, you know, n by k dimensions. So let's just edit this. Let's add a row, add a column. Okay, and we'll just add a column of zeros. So now, second, quit out of that. Okay, and I'm going to go back up here and ask it to do RREFA, and you'll see that it still gives me that identity matrix on the left side there. Okay, so all is good. Okay, we didn't break any fundamental rules. Okay, by adding on that zero matrix, or that zero vector on the end. Okay, so this is a way to prove, in quotation marks, that it is linearly independent. Okay. Okay. So the set of vectors are linearly independent. Okay. And so, you know, in this case, we would need three. We would need three vectors to span R3. Okay. Now we could span R3 with those three vectors. Okay. Number 2. Are the vectors v1, v2, and v3 V1 equals 1, 1, 1. Okay. Okay, V2 equals -1, or sorry, 1, -1, 0. And V3 is equal to 3, 1, 2. Okay. Okay, are the vectors linearly dependent or independent? Okay, or linearly independent? Linearly independent. Okay. So again, we're going to go C1 times V1 plus C2 V2 plus C3 V3 equals 0. And so this is going to be C1 times 1, 1, 1 plus C2 times 1, -1, 0. Okay, and then C3 times 3, 1, 2. Okay, equals 0, 0, 0. Okay. As you can see, the one, this one is going to be the first uh, coefficient in my first system, or my first equation, okay, in my system of equations. This guy's going to be the second one, and that guy's going to be the third one in my first. So I'm not going to distribute like I did in the last section, or in the last problem. I am going to just kind of write it out, knowing that I could kind of distribute in my head and then add them all up. So C1 plus C2 plus 3C3 is equal to 0. Okay, C1, this is the middle component. C1 minus C2 plus C3 is equal to 0. And then C1 plus 0, C2, okay, plus 2C3 is equal to 0. Okay. Okay, so what's my coefficient matrix? Well, it's just 1. A is equal to 1, 1, 3. Okay, 1, -1, 1. And then 1, 0, 2. Okay, so that's what A is. Okay. And so what is the determinant of A? Okay, I could plug that in. Plug that in the calculator. Second matrix. Oops. Okay. Second matrix. And we're going to go back to edit. With this one, let's make it into a square matrix because we can only find determinants of square matrices. And this is going to be 1, 1, 3, 1, 3, and then 1, -1, 1. Oh, that's still that. Oh, cool. And then 1, 0, 2. 1, 0, 2. Okay, so now let's find the determinant of this guy. Second quit out of that, and we want to find the determinant. So let's go second matrix, go over to math, hit determinant equals determinant of what? I want the determinant of A. Okay, of matrix A, not just A, matrix A. Okay, so matrix A. Okay, close parentheses, and it's 0. Okay, and so what does this mean? This means that one of those vectors is not unique. It's a linear combination of the other two. Okay, and we could see that by RREFing this thing. Okay, if I go up here and just steal this from before, okay, matrix A is my new matrix that has a determinant of 0. You'll see that I do get a row of zeros, which means that it was linearly dependent. Okay, if I get a row of zeros, it means that, I really only had 2 unique vectors. Okay, and the third was just a linear combination of the other 2. The third one was dependent. There's that word dependent. The third vector was dependent on the other two vectors. It was merely a linear combination of the other 2, and so it got eliminated when we did reduced row echelon form. Okay, and so we really had 2 unique vectors instead of 3, and so this is dependent. Okay. Oops, sorry about that. Okay, so the determinant is equal to 0, which creates a linearly dependent vectors. So the vectors are linearly dependent. Okay, also note, okay, that 1, 1, 3, 1, -1, 1, 1, 0, 2 becomes, okay, 1, 0, 2, 0, 1, 1, 0, 0, 0 after RREF this. Okay, and so it contains a 0 row. Thus dependent. So either way, it's dependent. Okay. The set of functions, okay, f1, f2, ... fk is linearly independent on an interval if and only if the only solution, so linearly independent, if and only if the only solution to the equation, okay, these are equations now, okay, not vectors. So keep that in mind. These are equations. They contain multiple variables in a certain dimensional space, but these are functions. Okay, if the only solution to the equation C1 F1 plus C2 F2 plus dot 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 plus CK FK equals 0 occurs again when C1 equals C2 equals the trivial case. It's very much a trivial case because you're like, oh, well, if all of the constants are 0, then it's going to go to 0. That doesn't really tell me anything about the functions. Could have plugged anything in there. Okay, but if they all go, if it equals 0 only when all of these are forced to be 0, okay, then it is linearly independent. Okay, recall. Okay, from previous videos. C of k of I, okay, this is all of the functions that have a kth derivative, okay, over an interval I, okay, a certain interval I. Okay, this is the vector space of all real valued functions that are continuous and have at least k continuous derivatives. Right? Okay, definition. Okay, let F1, F2, dot, 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 Fk, oops, Fk, be elements of C to the k minus 1th derivative, okay, of I. Why k items? Because we're not taking the derivative of the first guy. Okay, the first guy is the function. Okay, is a function. Okay, so we take k minus 1 derivatives, okay, of a function, of just a xy function or xyz function. Okay, we start with the function, which basically is the 0th derivative. And then we can take k minus 1 derivatives from there. Okay. So let F1, F2, Fk be elements of C to the k minus 1 over a certain interval I. Then the Wronskian of this set of functions is defined as the Wronskian W of F1, F2, dot, 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 Fk okay, of x. Okay, these are all going to be functions of x. Okay, is equal to the determinant of the functions f1 of x, f2 of x, dot, 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 to fk of x. Okay, and then, okay, we're going to take these guys and we're going to do k minus 1 derivatives on them. Okay, now will give me a k by k matrix. Okay. So I'm gonna do the first row is, again, is like the 0th derivative. Okay, and then the second row is the first derivative. So we do k minus 1 derivatives, and then we create a square matrix by taking successive derivatives of it. So the next row would be f1 prime of x, f2 prime of x, dot, 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 fk prime of x. The next row would be f2 double prime of x. Or sorry, not f2, f1. f2 double prime of x. fk double prime of x. And we would continue this down until we got f1 to the k minus 1th derivative of x, f2 to the k minus 1th derivative of x. Okay. Okay. And so however many functions I'm given, that will dictate how many derivatives I take. Okay, because if I was only given 2 functions to create a square matrix, I would only need to take 1 derivative. If I was given 3 functions, I'd have to take a second derivative. If I was given 4, I'd have to take a third derivative, and so forth. Okay, so the number of functions you're given will dictate how many derivatives you have to do. Okay, so this guy is f of k to k minus 1. There's dot dot dots in between of x. Okay, so we're going to take the determinant of that guy. Okay, and that is called the Wronski. Okay, theorem. Okay, if the Wronskian does not equal 0 for some, okay, and this is important, for some x, it does not, could it equal 0? Sure, it could equal 0. But as long as there's some x for which it's not 0, that's the key. Okay, for some value of x, if this thing is not equal to 0 for some value of x, okay, in an interval, okay, in an interval, I guess we could say, okay, then the functions, okay, are linearly independent on the interval. Linearly independent on the interval. Okay, if the Wronskian equals 0, okay, that does not mean that it's linearly dependent. It just means it's inconclusive. Sorry. It would be really nice if we could say that they're linearly dependent. We can't say that. Okay. We can just, oops, equal 0. We can just say it's inconclusive. It could be or could not be linearly independent. Okay. Okay, so let's see how this works in practice. Okay, number 3. Are f1 of x equaling to x, and f2 of x equaling to x plus x squared, linearly independent on negative infinity to infinity. That's the interval. Okay, are they linearly independent functions? Okay, so we have two functions, and we're gonna look at the Wronskian for this. Okay, the Wronskian is gonna be the determinant of x and x plus x squared, and then I'm gonna take the derivative. So this is just 1 and 1 plus 2x, right? Okay, now I want to take the determinant of this. Well, how do I take the determinant of this? Just use the operation for a determinant of a 2 by 2 matrix. So we're gonna, cross multiply across. So x times 1 plus 2x minus the other direction 1 times x plus x squared. Okay. So this is going to be x plus 2x squared minus x squared. Okay. And that's going to equal x squared. Okay. And that is not equal to 0 for some value of x. It's actually not equal to 0 for a lot of values of x. Okay, I could plug in 1, I could plug in 1/2. The only thing that doesn't work is 0, but it didn't say for all values of x. It didn't say for all values of x, then it was linearly independent. No, it said for some value of x between negative infinity and infinity, is this not equal to 0? And the answer is yeah. It's not equal to 0 for everything. Yeah, left off a C there. Okay, except x equals 0. We can't have x equals 0. Okay, but we can have anything else. Okay, so we say on negative infinity to infinity, okay, on negative infinity, f1 of x and f2 of x are linearly independent. Okay, that's good. So yes. Okay, so the answer to that is yes, they are linearly independent. Number 4. Okay, R f1 of x is equal to 2x squared and f2 of x equals negative x squared, linearly dependent or linearly independent? Okay, well, let's try the Wronskian. Okay, so Wronskian for this is 2x squared and negative x squared. Take the derivatives and I get 4x and negative 2x. So again, I'm going to find the determinant by finding my cross products. And so we get 2x squared times negative 2x, okay, plus 4x times negative x squared. And that equals negative 4x cubed. What did I do here? Oh, this is not a plus, this is a minus, sorry. Minus negative 4x cubed, which will be equal to 0. Okay, for all x. Okay, it will equal 0 for all x. It doesn't matter what x was on that interval, it's always going to be 0. The Wronskian is always going to be 0. So is this linearly dependent or independent? Well, it's inconclusive. The Wronskian is inconclusive. If we could find some value that it was not equal to 0, then it would be linearly independent. We'd know right away. Oh, okay. But this is inconclusive. But we can see that F1 and F2 are linearly dependent. Now how can I see that? Well, if we take F1 of x equals 2x squared, okay, and then F2 of x is equal to negative x squared. Okay, we can see that there is a linear combination, okay, that will get me 0. Okay, there's a linear combination here of these guys. Remember, C1 V1 plus C2 V2, does that equal 0? Okay, and if the only if the only value for C1 and V and C2 are 0, then it's linearly independent. If there is another value there, then for C1 and C2, then it's linearly dependent. Okay. So the way that we kind of set this up with these functions is I want to say that if I take 1 times my function 1, my f1 here, and then I do 2 times f2, 1 times f1, which is 2x squared, and then I do 2 times f2, which is negative x squared. Does that equal 0? And yeah, I'll get 2x squared plus negative 2x squared equals 0, and I get 0 is equal to 0. And so we can see that f1 is just equal to negative 2 times f2. Okay, and so they are linearly dependent. Can one of the functions be expressed as a linear combination of the other one? And yes, it can. Okay. Okay, I think we'll stop there. And that is section 4.5. I'll see you in the next section, 4.6. Okay.